Okay, I might get started. So thanks to everyone for coming to today's ARC Center of Excellence for Enabling Eco-Efficient Beneficiation of Minerals signature lecture. We have Professor Aaron Noble from Virginia Tech here to talk to us. And before he starts, I'd like to acknowledge the traditional custodians of country throughout Australia and their connection to land, sea, and community. And we pay our respect to the elders, past, present, and emerging, and extend that respect to all Aboriginal and Torres Strait Islanders and other native people throughout the world. And so Aaron is a partner investigator of our center and working professor in Virginia Tech. And he's going to talk to us today about recovering rare earth elements and critical minerals from unconventional resources. So I'm looking forward to it. Thank you, Aaron.
All right. Thank you so much, Professor Franks, and thank you to the entire center for inviting me and letting me give this great signature lecture. Really looking forward to it. And as Professor Franks mentioned, we'll be talking about rare earth recovery from unconventional resources. So let's just jump right in. I wanted to start by introducing myself a bit and introducing Virginia Tech. So if you've never been to the U.S., I want to offer you all an open invitation, everyone on the call. Please come visit us. Please come visit us at Virginia Tech. Here's where we're at. We're on the eastern side of the U.S. Driving distance is about 4 hours south of Washington, D.C., maybe 6 hours south of New York City. As we said, leading up, I think many people will be in the IMPC conference in Washington, D.C. It's at an absolutely fantastic hotel next month. If you have interest in time, I'd love to have you. So just let us know. Here's where we're at on the map. Here's our beautiful campus nestled right here in the Blue Ridge Mountains. They call them the Blue Ridge Mountains because the trees emit some gas that makes the texture actually look blue. My building is right here. So we're right here, right in the middle of campus. And Virginia Tech is what we call in the US a land grant university. And the land grant tradition was one meant to serve kind of the working class. So it started as an agricultural and mechanical school, mainly doing ag science and engineering. And fortunately, mining engineering, my program was one of the very first at the school. Right now, I like to say we do everything at Virginia Tech at tremendous scale. So if you look at our total undergraduates, we have somewhere around 35,000 undergraduates, over 10,000 total engineering students. So when we have a commencement ceremony, it literally takes 8 hours of commencement to push forward a graduating class. My department is very small, so we're one of the smallest in the college, but probably one of the bigger mining and minerals programs in North America with 117 students. That would be sophomores, juniors, seniors, and graduate students. We currently have 9 full-time faculty, and I want to encourage everyone. We'll be opening a new faculty search in the area of critical minerals later this semester, so keep an eye on that. Here's another picture. This is the last one, I promise, of our great facilities. So this is our mining engineering building. We actually just moved into this 2 years ago. So the university was looking around campus and decided that we would be a good target for investment. So they tore down our old building and built us a new one to the tune of about $70 million US. And here's some examples of some of the spaces. So we've got a nice open high bay like model mine here where we can fly drones and do some drone-based surveys for students and for research. And here's some sort of open classroom space area, learning space where students write their notes in the whiteboards and you can walk by and criticize them. It's really good. So shifting gears to looking at critical minerals, I wanted to start a little bit differently. So I've been reading this book recently, and it's a really good classic book about corporations and how corporations can make the turn from being an average company to being a great company. And Jim Collins is a really exceptional author, and he does this in a very rigorous manner where he looks through like 200 years worth of stock data and tries to pull out commonalities of what makes a company turn from good to great. But while reading this, there was this quote that really struck me. And I'll just read this out loud for all of our benefits. And it says, every good to great company faced significant adversity along the way to greatness, one sort or another. In every case, the management team responded with a powerful psychological duality. On one hand, they stoically accepted the brutal facts of reality. On the other hand, they maintained an unfavoring faith in the end game and a commitment to prevail as a great company despite those brutal facts. And I really think this is how we should model our R&D programs. And this is also how we should model like the whole impetus to produce critical minerals, right? There are brutal facts of reality that we cannot escape or evade, but we have to understand and we have to interrogate them and we have to challenge them. But through our research and technology development, I think we have to, at the same time, keep unwavering faith. And so this will be a theme of this presentation, this kind of dichotomy of brutal facts and unwavering faith. And hopefully we'll go through this journey together. So here's how I've planned it out. Start off, we'll talk a little bit about some scoping the critical minerals problem and seeing what type of challenges we're up against as a society and as an industry. We'll then shift into what I would call the more depressing part of the conversation, where we'll look at some of those brutal facts and really question what is possible. And I say economic realities, and there's some technical realities of what we need to do if we're going to produce rare earths. And then finally, we'll talk about a couple case studies of technical solutions that I think should give us faith in the long term. So setting scope and expectations. Many of my presentations, I like to start by asking the question of where does mining fit into society, right? And a good place to look is to the UN sustainability goals. And I think now, when I started this several years ago, many people didn't know about these, but I think now they're pretty familiar. A lot of companies are posting this, and I think there's a lot of information out there. But I like to say, it was about a decade ago, a bunch of people a lot smarter than me got together and said, if there are great things we want to do as a global society, what are they? And they came up with these 17 items. And I think it's important to look, and it's funny, I was talking to a colleague today, and they said they went through all the documentation on all the UN sustainability goals, and the word minerals doesn't come up one time in the documentation, which is sad. Because if we look at all these things we want to do, economic things like no poverty, environmental outcomes like protecting land below water and on land, protecting wildlife, and then social things like quality education and gender equality, they all require materials, and those materials have to come from mining. So I usually like to show this depiction instead, right? This is the same 17 goals, but right here in the middle, we have a mining symbol. And then the larger slices of the pie are ones where we believe mining has a very, very strong impact to influence the goals. And if you look across many industries, there's not many that have such a wide and broad impact across, I think this is like 11 or 12 goals. And I think this needs to fuel and kind of motivate us as researchers and engineers to understand how we're contributing to society. Technology minerals are a place where this becomes ever present, and we have to start thinking about what are our goals as society and what are our trade-offs and what trade-offs are we willing to accept. And so there's a lot of good data out there from IEA, International Energy Agency right now, that if you've not had a chance to look at recently, they've put in some really, really amazing data viewers where you can go slice things different ways. But they've done a good job of analyzing the mineral and material needs for new energy technologies. And this is an example of one of those where they looked at a conventional internal combustion engine vehicle, and they looked at a conventional electric vehicle or current electric vehicle, and they looked at the mass, just the raw mass of what I would call exotic metals that go into these different types of vehicles. So they've taken out aluminum and iron because those would be a big portion of the mass, and just looked at exotic metals. And you can see that something like an EV requires 6 times the amount of metal as a conventional vehicle. And then I also like to point out that there's different flavors on this one too, right? Different colors of the rainbow. So it's a larger selection of exotic metals that are needed. And IEA does this for a number of different technologies, from grid storage to photovoltaics to onshore and offshore wind. And you see this type of trend develop. Another way you can slice this data set is looking at the materials and then summing up what you would need for any type, all the energy technologies put together, just how much more are we going to need to produce. And they present this in a little bit of a confusing fashion, but this is the essentially 20-year growth index is what we're showing on the y-axis. So pegged to a 2020 base. So in 2040, how much more material are we going to need relative to what we were producing in 2020? That's the way you want to think about this, with the higher end of the bar being the most aggressive sustainable energy transition, and then the orange one just being if people do what they say they're going to do. And obviously here you see a high concentration in battery materials. So lithium, graphite, cobalt, and nickel, with lithium being a 42x increase, right? We're going to need 42 times the lithium in 2040 versus what we need in 2020, which is just absurd if you think about it. And if you think about how much Earth's going to have to be moved to produce 42 times the lithium, some of these things start becoming astounding. And I say without hyperbole, right? I think we're on the doorstep of a mineral revolution. That's what we're going to need to get to these type of production levels. But to give you something a little bit more meaty that you could chew on, I've also seen some analysis done. If we just take the battery materials, for instance, and there's a group called Benchmark Intelligence that looked at this in a little bit more granularity. They said to produce these battery minerals, we would need 300 new mines in the next decade. So in the next 10 years globally, we're going to need 300 new mines in these four commodities to produce these type of materials. I think if prior performance is a prediction of the future, this is quite a feat to get to. Nickel is another one, and I did a calculation here and said if we produce nickel in the manner in which we've always produced it, what would be the CO2 generated? And what would be, the contribution to global warming just from nickel production? And when you add it up, it's like once we're at that 20x growth index, once we're at the 2040 amount of nickel being produced, the nickel industry alone would be about equivalent to the country of Sweden in terms of CO2 emitted. And then you start getting down the rabbit hole of what other environmental impacts would come from these type of activities. Another one I don't show here, but I've had a good colleague tell me even copper down here, copper critical for any electrification, but pretty low on the growth index scale, right? We use a lot of copper. There's a lot of copper in the ecosystem, maybe a 3x growth, which is pretty typical over the last couple, decades for copper. What that means in terms of real numbers is a tier 1 copper asset coming online every year for the next 2 decades. So a tier 1 copper asset every year for the next 2 decades to get to this level of copper by 2040. Like I said, mineral revolution is before us. And then you start looking at what's the status right now. And this is probably a graph many people have seen, but if not, I really like to highlight some parts on it, because we like to think of fossil fuels, in particular oil and natural gas, as being political commodities, as I would say, right? Very politicized commodities. And I didn't know how things are in Australia, but the gas price is always a hot topic this time every 4 years when we're leading into a presidential election. So it's very common. But if you look at it in terms of raw numbers, and what this shows is the percentage of production that the top 3 producers contribute to. Oil and natural gas, your top 3 producers get to, 50% of the extraction and then maybe 50% of the refining capacity. If you look, though, at minerals, right, you can think about cobalt, right, where the DRC controls almost 70% of the mining and extraction, and then China controls over 60% of the, the processing and refining. And you start to see the potential to politicize a lot more than just fossil fuels, but a lot of minerals. And if we think about the energy transition in a way of transitioning from a fuel-based energy system to a mineral-based energy system, we start to see how these geopolitical dynamics can play in and scope the type of technical challenges that we need to face. I'll be talking a lot about rare earths, so I did want to highlight those in particular. I did title the presentation Rare Earths and Critical Minerals. Spent about the last 10 years focusing very heavily on rare earths, and then we're doing a little bit in battery minerals. So we'll kind of target rare earths, but you can see rare earths kind of known to be produced significantly in China, with about 40% of non-Chinese production. the US and Australia being the other two large miners, if you will, but China controlling almost 90% of the refining capacity, and then almost 100% of all the downstream manufacturing that uses rare earths. So this kind of feeds into this notion of criticality, right? And so I've showed you some data saying, hey, we're going to need a lot more of this stuff. And obviously that's a component of criticality. I've also shown you data that we currently produce this in very narrow supply chains that are controlled by just a handful of companies. And so, or countries, excuse me. So we understand that there's a notion of these materials are critical, right? And over the last, I think, 5 to 10 years, you've seen a lot of governments and agencies start to develop their own definition of what is criticality. In the US, we're kind of governed by the US Geologic Survey's methodology. And I recall very ironically, I was talking to a news reporter a couple years ago, and they were like, tell me about critical minerals. I don't remember studying those, that set of minerals in chemistry. They're like, is that a scientific term? And I was like, no, it's actually a legal term. Like in the US, critical is defined by the government, right? It's defined by the US Geologic Survey. And so they use a quantitative, it's a very rigorous methodology that essentially considers disruption potential, trade exposure, and economic vulnerability. So disruption potential would be things like single points of failure, how many different companies and countries are involved in the supply chain that would contribute to your DP index. Trade exposure is just straight up US import reliance. So that's TE. And then economic vulnerability, it's a little bit complicated, but they looked at a host of manufactured goods throughout the US economy, and then they traced it back to the minerals contributing to those goods, and they looked at the market value of those minerals. And from that, you take the geometric mean of those three, and that produces a ranking, if you will, of what are the most critical elements. And so one way you can plot this, we've plotted it here as two axes, but you got to think about the third axis here as well. That's demonstrated by the size. So economic vulnerability on the Y, disruption potential on the X, and then the size of the bullet represents your trade exposure. And through this methodology, you can see that the US considers actually gallium to be the most critical. Cobalt is very high too. I think cobalt's 2 or 3. And then also you start seeing some of the rare earths pop up: neodymium, praseodymium, dysprosium, lanthanum, and then a number of other exotic metals come up too. I like to show this though, because this came through, like I said, the USGS spent a couple years, I think 2 years, developing out this methodology, but then you can use this as a means to inform your strategy, right? So if you're going to develop a strategy or an R&D strategy around de-risking the supply chain, you just need to pull one of the legs out of this three-legged stool, right? And so we've developed a strategy in the US that kind of centers around two major aspects, one being developing substitutes and one being diversifying supply. If you read a lot of US critical mineral strategy, they'll include recycling in there, but I would consider recycling a subset of diversifying supply. So the strategy kind of hinges on these two major components. Substitutes are things, for example, like low rare earth magnets, right? Can you make a magnet that uses more common materials? Can you make a battery that uses more common materials? I have a sister department downstairs, my material science and engineering department. That's what these folks do all day and all night. They look at alternative formulations of materials. Being in mining and minerals engineering, I consider myself here on the x-axis, diversifying supply, right? If we can identify other means of producing these materials, then you'll naturally move them to the left in the plot, and then potentially shrink the size of the bullet as well, reduce your trade exposure, and then through that reduce your overall criticality. So instantly, when people think of supply diversification, one of the things we immediately like to start thinking about is our byproducts. Can we start producing these materials from byproducts? And there's a couple of tools we can use to evaluate if the byproduct route is the way to go. And I think this data is actually pretty helpful. I found this was the 2022-2023 Critical Minerals Report by Steve Fortier, who's at USGS. And I actually love this plot. So what it's showing is the global annual production of various mineral commodities. And then it's showing what the price is, like a typical price normalized to a unit ton of metal or of material, right? And then he's color coded it by red being byproducts and blue being primary products. So you can plot all these up, you start to see some trends develop, and you can draw these lines, which are constant market cap, essentially. And it's pretty cool because you can see that things like the gold market, right? The global gold market is about the same size as the global copper market, the global aluminum market, the global iron market. They're all about, a couple $100 billion markets. If you look though at a lot of these rare earths, right, you start to see things like, lanthanum and cerium, $100 million each. Yttrium, you're talking about like tens of millions of dollars. Like these are not massively, massive, large commodities in terms of their impact as a raw material in global economy. The question, though, is then how much economy do they enable downstream, right? If you're able to build a rare earth magnet, what does that enable downstream on the manufacturing side, not just what the raw commodity enables? But one thing I noted here is if you look at it about 10,000 tons, right, everything below that becomes more of a byproduct. And a lot of the critical minerals we would say, hey, are in this range where they are likely being produced as byproducts and should be considered as byproducts if we're looking at opportunities for supply diversification. The next crazy plot I'll show you, and then we'll stick to some more conventional ones. If you've not seen this before, this is actually an absolutely genius way of plotting this, and I love this, and this is why I show it. It's called the wheel of metal companionality. It's also often called the Gradle wheel. So Gradle is a professor at Yale here in the US, and Nassar's with USGS. And what they did is they looked at like 60 or 70 different mineral commodities, and they evaluated to the extent they were produced with other mineral commodities. And that's what they defined as companionality, a degree to which a metal is obtained largely as a byproduct of some other type of ore. And they found that the majority of metals that we use in terms of number of metals are actually produced as companion metals. And so through this analysis, they came up with this plot, which in the center, you have your big producers, your primary metal products, things like aluminum, copper, iron, titanium. And then as you go out the wheel, it tells you how much of the companion metal is produced as a byproduct of the major metal. So a good example here is gallium. Gallium sits almost at 100% with aluminum. So almost all the gallium that's produced in the world is produced as a byproduct of aluminum. Vanadium, on the other hand, is pretty far out. We'd say 20% of the vanadium in the world is produced as a byproduct of aluminum. So how close something is to the center means how closely associated that commodity supply chain is with the primary element. Said a different way, if you control the aluminum market, you by extension control the gallium market, right? If you control zinc smelting, you're probably going to control the vast majority of germanium production. And that's the way you can kind of read this. Are these things close, or the ones where you see companion metals being produced? What jumps out to me, though, as somewhat problematic is if you look at the rare earths, we know rare earths are small commodities produced largely as byproducts, but they don't sit close to the center on any of these wheels, right? You'll see some rare earths produced as a byproduct of titanium production, say from monazite sands in titanium production. But if you follow the wheel around, that's 10% of global rare earths, right? This says a little bit also as well. Some of the lanthanides are produced from tin. I'm not sure where that's happening, but it may be happening to a very minor extent. So if you carve all this out and you look at the rare earth market, you see from the slide a couple of slides ago, high geographic concentration, mined and processed largely in China, not really associated with a major ore, right? There's not like one major ore we could go to and start pulling these out from a byproduct, and almost no end-of-life recycling right now throughout most of the globe. And so I say these three kind of make them an ideal candidate to look at unconventional resources. If you genuinely want to diversify the supply chain, this is probably a good area to start looking based on these, these factors that are playing in. Other critical minerals, there may be different production routes where you could look at byproducts and things like that. I like to think rare earths, because of these factors, make them somewhat a very interesting source for an unconventional resource development. And by and large, there's not like standard definition of unconventional, but I generally refer to it to mean not an ore, right? Not a typical rare earth ore, but some other type of source would fall under the domain of unconventional. Before we get too far ahead of our skis and start talking about how we're going to go start extracting rares from all these unconventional resources, I think it's prudent to take Jim Collins' advice and let's look at the brutal facts and see what the brutal facts of the rare earth market tell us we have to do. And a couple years ago, I had a great opportunity to write a book chapter for this book, Rare Earth Metals and Minerals Industries. My colleague Rohan Yoon, who many of you may know, he wrote a chapter as well. It was just released this year, like it was just published this year. If you get an opportunity, highly recommend it. It's a good book, covers a lot across the rare supply chain. I got to write a chapter on the economics of rare earth processing from conventional and unconventional feedstocks. And what I did in this to kind of set the baseline and do the recollection of the brutal facts is I wanted to see what the investment landscape looked like across the world in rare earths. And what we see in the rare earth market is if you go back to the early 2010s, as many of you may know, there was a big price shock due to a Chinese-Japanese trade, essentially trade war, right? And through that, China set up a quota system. They restricted the export of rare earths, and prices went up, 10, 20-fold overnight. So we have this price shock of rare earths, and that's when everyone became alarmed, like, what are we going to do if we don't have these? And then what happened after that, as recounted by my good friend Clint Cox, he wrote this article you can check out. He published it in 2018. Clint Cox is an absolute genius on rare earth markets. He looked at all the investment capital raised and calculated almost to like a very high degree of precision how much investment capital was raised for junior mining companies in the early 2010s as a result of the price shock on rare earths. And he found about $4.2 billion. And so what I did in the book chapter is I took the next step and went to all those junior mining companies and pulled their public reports and then started to normalize the data in those public reports to get an idea of what the investable landscape looked like, what is out there. And so through this period, they raised $4.2 million. And I found about 40 to 50 rare earth development projects at some stage of public disclosure. 21 of these, they would have some resource estimate. 21 were at the stage where they would have some preliminary economic analysis or some economic data. Fortunately, through this, we were able to find globally 45 million metric tons of measured, indicated, and inferred resource, or about 200 years of current consumption. So we raised all this money, $4.2 billion of invested capital, and we found about 200 years worth of rare earths. I then took the next step to say, okay, what do the economic indicators look like? Surely these have to be pretty good, right? Rare earths were doing well. We said 20 of the 21 projects, every single one of them, as you can imagine, showed favorable economics, some with what I would call extraordinary economic indicators. And here's some box and whiskers that I show. So one, just what was the grade, right? Like what grade were they using? What was their average grade? You can see the median here at about 1%, average between 1 to 2%. One extreme outlier, like 14%. They had found an ore body that just sat at 14% rare earths. But this kind of tells you what is a good resource. Maybe 1 or 2% was considered investable in those days. Translated then into what their rate of returns were, we see going from, say, 16% up to 50% rate of return. The challenge is, though, and as Clint identified and as I identified, $4.2 billion and not a single kilogram of rare earth was produced from any of that. None of these were brought to production. The only thing that came out of any of this was the Lynas mine in Australia, right? And they're doing very well in producing. They're not included in this analysis. They're not part of the $4.2 billion. This is everything else. Not a single mine was brought to production. And that begs the question, why? Like, why did this happen? And it's pretty interesting in the way we do these economic analyses. If you look at the year these reports were published, so this is just a simple bar graph showing the year that the reports were published, the ones included in my analysis, a lot in this 2011 to 2015 range, which coincides roughly with the price spike, right? So this is like dysprosium spike where it went up, to some indicator much higher than the baseline, and then it took about a year to cool off. And often what you find in these public disclosures are that, for better or worse, the companies will use 3-year trailing price averages, sometimes 5-year trailing price averages. So if you're sitting in 2015 using a 3-year trailing price average in your analysis, you're going to capture some of these elevated and unrealistic prices. You fast forward to more stable market conditions, and these become uninvestable projects. But we can dig into that a little bit. So here's some of the data that come out of that, and I usually like to use this. Like I said, these are the brutal facts. These are what it costs to build a rare earth mine. So if you look at the investable landscape and you look at your tons per year of rare earth production, it fits pretty nicely, to a curve corresponding to capital cost, right? A power curve corresponding to your capital cost to develop that site. So of the ones evaluated, we went everywhere from $100 million at low production, right? $100 million of CapEx to get a low production small mine, up to, almost $1 billion to build one of these massive large mines. Similarly, you get a little bit of economy of scale, and that's what this curve is showing with the OpEx. So your low, small producers tend to have higher OpEx, and as you build larger and larger mines, you can decrease your OpEx, somewhat substantially. Here's another plot I've generated that I thought depicts the situation quite well. This is kind of the cost curve, right? And you'll see these for a lot of mineral commodities, usually for producers, but this is instead for potential producers, and each one's labeled. The width of the bar is proportional to their annual production, and then you can see where they sit on operating costs going up the cost curve. The brutal facts, right? The best I could tell, that's about what the width of current Chinese production would look like, right? So it would require almost every single one of these sites to completely offset what the Chinese are doing right now. And we could add up what that total CapEx investment would need to be to offset Chinese production. They essentially cover the entire cost curve if you overlaid current Chinese production. The other one, while there's not a lot of transparency, the best we can tell, Chinese costs are often less than $10 a kg. It's single digit production costs. So if you start laying these over a economic reality, very few of them look cost competitive against the Chinese. And so you have to then question and challenge the assumptions and how we would go about deploying this if these are the brutal facts of reality. This is another way I like to plot it, because this makes it very poignant and kind of demonstrates the principle. What this plot shows here is it's kind of a cost benefit plot. So on the x-axis, we have the reported operating costs that they had in their report, and some of these I had to normalize to a consistent basis. But this is their dollar per kg production cost. And then on the y-axis is their dollar per kg of sales price, which in rare earths we call the basket price. So this is how much money they can make from selling a kg of product. This is how much they're going to pay all in to produce that kg of product. And you can draw lines of constant margin. And you're like, dang, Aaron, they're making like 75 kg margin. That's like a 80% gross margin, right? Like that's surely profitable. It's quite amazing if you think about it. What I did in the analysis is I took this and showed it as a function of reported prices, and then I showed it as a function of somewhat contemporary prices. And you can see just about all of these, deposits sink down to the break-even curve or even go below. So in current economics, these are marginal at best and downright unprofitable at worst. That's a depressing slide, I know, but this is the reality of trying to produce in the rare earth market. It's incredibly challenging with high barriers to entry. Another one I want to show you, just to depict, and this is my good colleague at University of Kentucky, Rick Honaker, likes to show this. If we look at just a mass balance, right? Like we're process engineers and we like to think in terms of mass balances. What does processing a typical rare earth ore look like? Right? Like what are they doing in China? What are they doing at Linus and at Mountain Pass? You may have something like 100 tons per hour is your concentrator feed. You may be processing material out of the ground that's like 10% rare earths. This would be very rich on our scale of prospective deposits, but we can adjust this, adjust our minds to what to the actual feed grade. And you're going to go through a series of beneficiation, grinding and flotation, roasting and leaching, some sort of solvent extraction or separations, some precipitation recovery, and then out the back, you might get something like 8 tons per hour of rare earth, rare earth oxide at a pretty high grade. And if you equate that on an annual basis, that's 48,000 metric tons of rare earth oxide. And I think these numbers are tied pretty close to what Mountain Pass does, right? And what they report that they're doing is what a typical, simple BFD would look like for Mountain Pass. If we instead do this for a low-grade unconventional resource, and we apply some typical assumptions, the numbers start to give us a little bit of heartburn, right? So say we're going to process mine tailings, and we have something like a coal preparation plant that's producing 500 tons per hour of reject. Maybe that's around 300 parts per million. We'll do our best to concentrate that and to pre-concentrate it and increase the grade. We'll talk a little bit more about this later and some opportunities we have there, but you'll do your best there. You'll then do some sort of solution, leaching or extraction, purification, precipitation. Perhaps this may be in a more difficult to recover form, so your system recovery is a little bit lower. And you've gone from producing something like 48,000 metric tons a year to 230 metric tons a year, right? The scale of what you need to move and process changes significantly when you look at a low-grade feedstock. And that's sobering, but it tells us how we need to think about the problem, right? And that's where I wanted to shift gears, right? This is the low point of the presentation. Let's shift gears and make this a little bit more enthusiastic. What are some pathways that make sense? And this plot right here, I'll dissect this for you, but this is the single biggest point of what I would call unwavering faith in the whole presentation. This gives me hope that our R&D solutions are going to yield something out of necessity. And what this is terbium and dysprosium projections, estimated supply and demand. And these are considered some of the most critical rare earths. They're both heavy rare earths, and you'll see in the numbers produced in very scant quantities, but absolutely essential for high temperature magnets. And high temperature magnets used in a lot of energy applications absolutely require TBDY. And I've worked with some defense suppliers who absolutely have to have this material. If you look at what happened last year in respect to just TBDY supply chains, you can see here, this is just a waterfall plot adding up where all this comes from. You have hard rock sources and ionic clays. Ionic clays are the most renowned source of heavy rare earths in the world, and they contribute about 1,000 tons of TBDY. Added up, that gets us to 1,500 tons of what we would call Chinese official production. In addition to that, you have about the same amount of what we'd call unofficial production or unsanctioned production, or perhaps imported production. Just generally, that is about to double the amount of the official production. Serra Verde is a Brazilian site that's coming online. It's adding a little bit of TBDY, but going to China for processing. So that gives you a total amount of Chinese processed TBDY of about 3,300 tons. The US and Australia add like I said, a scant amount, about 100 tons per year of potential at MP Materials and Linus, maybe some other ones. That gets us to an estimated global supply of 3,400 tons of TBDY. If we fast forward a decade, how much TBDY does the world need? We need about 8,000 tons based on projections, right? And this slide I clipped from this company that's developing a heavy rare earth mine, right? A heavy rare earth project, and they say we can contribute 250 tons, and they say that's significant, right? It becomes about 6% of the supply gap, and that tiny amount becomes significant in this grand scheme, especially when you're staring down a supply gap that's bigger than the global market right now. So I say that you kind of get to wash away all those things about volume and cost, because this is absolutely going to have to come from somewhere, right? And it's going to require all the feedstocks and all the options we can generate and we can come up with as a mining community to meet the supply gap, to meet the critical needs for TBDY. So looking at this is a fact as well, but this is a fact that gives us a lot more hope. In the US, we took a strategic approach to begin looking at mine wastes, and we started in the coal basins and looked at coal wastes as a potential source of rare earths, and particularly heavy rare earths. And if you're not familiar with the coal producing regions of the US, this is a map showing that. Like I said at the beginning, I'm about here. So we sit right at the foothills of what we call the Appalachian region. It's known for some bituminous coals, so bituminous and then anthracite in the northern Appalachia, but bituminous and anthracite. You have other bituminous regions in the Midwest and in the far west, and then you have some lignite and some lower subbituminous coal out west as well. So just to level set as we talk about it, I'm going to be talking quite a bit about Appalachian coal because that's what we're most familiar with. And when we started this several years ago, this is a good example of what a stratigraphic column of coal looks like for an eastern coal seam. And you can see the inner layers of coal and clay and shale that kind of feed up through the whole what we call the coal measures. And one of the things we looked at and we found very, very quickly is that the rare earths are actually not associated in the carbonaceous material, but they're actually in the clays and shales immediately above and below. That's where we get the largest concentration of rare earths. And so you can see, for instance, in this particular coal bed, we found concentrations almost up to 800, 900 parts per million, which gets you close to what would be on the lower end of a very viable resource in the clay immediately above the coal, and then maybe 600 in the clay immediately below the coal. So I just say this to say when we talk about rare earths in coal, it's generally partitioning with the clay fraction, not with the carbonaceous material itself. And this allows us to begin asking some like very basic assumptions, right? And this is a cartoon I generated that I think gets to what the vision could be and what the vision for the mining sector could be. And if you look at like a traditional coal mining value chain, you know, we take it from a coal mine underground or surface, you go to a beneficiation plant, you're going to make some refuse or some impoundments. Some of it's going to get pulled off and go to coke production, but the large portion, we're going to burn it and make electricity and eventually put it into a fly ash pond. I drew this to show what possibilities could exist out there, right? If we really thought about taking the resource that comes out of the ground and squeezing it for all the value that's in it, right? Like squeeze every ounce of value out of it. What could happen here, right? And some of these may make sense, some may not, but let's run this thought experiment to see what it looks like. And I think the analogy that I think they do an expert job is the oil industry, right? When a barrel of oil comes out of the ground, they squeeze every last drop of value out of it. And I'd like to think the mining sector can begin a vision of doing the same. So I drew this up for what this might look like for coal, right? You still have a significant portion to power generation, but you may pull off a very high quality carbon that could be used for high value carbon products like carbon foam, carbon graphene, carbon graphite, construction materials, like some very high quality carbonaceous material. You may have some other, you know, the mineral component after you do the beneficiation. There may be some really enriched rare earth critical mineral concentrates that could go to like a rare earth refining or a mineral extraction. You may have some lower grade feedstocks that could go to something like a heap leach. Could we then take all this water that's coming off all these and then treat that acid mine drainage while also producing some critical minerals? Could we go back and look at these coal combustion byproducts and take what beneficial use is currently being done and identify others? And then there's some really crazy ideas like, can you take low quality fuels, right? Do like a fluidized bed combustion, capture the off gas, generate acid from the off gas, and then also create feedstocks that could be used for rare earth recovery. Pretty much every block on here, someone in the US is investigating right now. There's some research group that's looking at these as potentially viable options. I wanted to focus on 3 case studies I've had the opportunity to work on, though, and we'll go through these somewhat quickly because I do think these paint some very viable pathways. The first one I'll talk about, I've worked on for quite a bit, is using acid mine drainage as a feedstock for rare earths and critical minerals. And I've marked my collaborators here, mainly led by Paul Ziemkiewicz at West Virginia University and Tommy La Rochelle with L3 Process Development. If you're not familiar with acid mine drainage, it's like the most common industrial pollutant in many mining districts throughout the world. And it all starts with pyrite. So here is, for instance, a chunk of Appalachian coal with a big piece of pyrite sticking in it. Pyrite oxidizes, creates sulfuric acid. sulfuric acid, then and it's through oxidation and bacterial interaction that it generates sulfuric acid. That can then dissolve other metals in the host rock, predominantly iron and aluminum. And sometimes you'll get these iron outflows that contaminate the river and look pretty bad. What we found, though, is through that dissolution process, it's actually carrying rare earths with it as well. So there's rare earths that are existing in the coal strata. When the acid mine drainage leaches, it's doing so over a long time horizon, and it's taking rare earths and other critical minerals with it. So a couple of years ago, back in 2019, we did a pretty detailed study of about 200 sites throughout Appalachia, and we evaluated what the rare earth content was. And we looked at the distribution of rare earths in all these samples. And what jumped out very prominently are these very, very high dysprosium terbium signatures. And this may not seem like much, but as far as rare earth goes, having 6% dysprosium and 1% terbium would trump any conventional ore out there. This is an enormous terbium dysprosium potential. And when we think about making up the supply gap of terbium dysprosium, this acid mine drainage in Appalachia can overcome a pretty significant portion of that based on this very favorable rare earth distribution. So with that in mind, we kind of developed what a national supply chain would look like, where we would have various mining districts throughout the U.S. And I know this slide's very busy, but we'd have these various mining districts throughout the U.S. where we would pre-concentrate and then have like regional concentrators to start the upgrading process of acid mine rare earths from acid mine drainage. They could then feed into a central refinery where you do your separations and final product deployment. So we have this kind of broken out. And this was one of the keys to the process, is we developed kind of this patented way of simultaneously concentrating rare earths from the acid mine drainage, from the liquid into a solid phase, while also treating the water to a point where it can be successfully discharged. And this is a pretty simplified diagram of it, but we used a two-stage precipitation process with lime. In your first cut, you can precipitate a lot of the garbage elements like iron and aluminum. And then what you find is once you dial that in, you can generate what we call a rare earth pre-concentrate that approaches about 1% rare earths. So you take a raw AMD sample that may have parts per million or hundreds of parts per billion rare earths. You do this pretty simple process that you have to do anyway to treat the water, and you generate a concentrate that's almost 1% rare earths. That then becomes your feedstock for how you then derive concentrated rare earth products from that. And you can see there's some other good stuff in here as well: cobalt, nickel, manganese, lithium, and zinc. We have potential pathways to recover these as well. So we took that concept at West Virginia University and we built a commercial demonstration of this. So what you see on the right is the two-stage precipitation process, and this is the site it was deployed at. They're treating up to 1,000 gallons a minute of acid mine drainage here, and we were able to deploy the process. We then deployed a further processing behind that to dewater the pre-concentrates, leach and precipitate them, and then concentrate them into these two high-value products. So this is a 95% pure light rare earth oxide, and this is a 95% pure heavy rare earth oxide that we've been able to demonstrate at the plant here at West Virginia. Moving through a little bit quickly, but this was one example where we were able to take that pathway of taking a waste liability of acid mine drainage, developing a technical solution that kind of fits into what's going in, right? It fits into this, like, we have to treat the water anyway. Let's do it in a manner that allows us to simultaneously capture rare earths, generate these valuable products. And then we wrote a paper a couple of years ago on what the techno-economic analysis of that would look like. And we found for most pricing scenarios, and then these are different product scenarios, that it actually generates a pretty viable positive net economic impact, right? And you can see here, for instance, this last bar was one of our favorite ones because this is mainly based on terbium and dysprosium. Apologies for the coded x-axis, but this is mainly based on terbium and dysprosium. And you can see that we're generating net present values of $100 million to $200 million in the more favorable economic scenarios. And so it tells us that just based on those magnet critical elements, terbium and dysprosium, acid mine drainage can be a viable source and one that's economically attractive. We also thought in here we did an LCA as well, life cycle analysis, and kind of looked at the CO2 generation potential, and early estimates show it would be like 50% as impactful as traditional rare earth production. Another one I want to talk about real briefly, I realize we're closing in on our time, is recovery of rare earths from clay materials.
Don't be too stressed. Most of us can stay a little later. Yeah, I think it's okay. We can follow the discussion a bit later. Yeah.
Okay, excellent. Thanks, Professor. That's good to know. So I will push onward. So one I want to talk about as well, another potentially viable pathway, because you start to see what the constraints are and what your technical constraints are and the space you have to work in, and then some solutions that weren't obvious before, I think, become obvious. And really want to acknowledge my great collaborators here, Dr. Rohan Yoon, who I have spoken before at this event, and I think many of you know, and then Dr. Mohit Gupta, who's a research scientist, and I think he's on the call right now. So if we have any tough questions, we can let Mohit answer those. And then obviously all of our students and other researchers who've helped with this. Looking at the rare earths in clay, I want to go back to a slide we looked at a second ago, or rare earths in coal, I should say. I think Dr. Yoon, I'll give him credit, he realized very early that the data suggests and the data indicates that all the rare earths are partitioning to the clay minerals that are in the non-carbonaceous fractions of the coal measures, right? And this was one of the indicators of that we recognized very early, is if you look at the total rare earth concentration of a coal-based material, and you look at the total aluminum concentration of that same material, you get a pretty good correlation. And oftentimes the aluminum in coal is associated with finely disseminated clays. And there was a report put out by a geologic firm in the US that pretty much showed this data and showed the abundance that would be in things like kaolinites that are associated with the coal-based clays. And so using that as our assumption, and you can also see this data too as well, right? We see the really high rare earth contents in the what we call the overclays and underclays, right? The material directly above and below the coal seams. And so that led us to say, hey, the rare earths are in the clay. So if we want to find a way to extract and recover those, we need to have ways of processing the clay. The challenge is, and I was going to show it here, but then I took it out, the rare earths in those clays get to be very, very fine particles, usually less than 5 microns, sometimes single-digit micron, like 1 or 2 microns, right? And we've used SEM on a number of samples and identified rare earth grains that are associated with clays, and the clay is very fine. The rare earths on the clays are even finer. You're talking about things that are 5 microns or less. And that creates a real technical difficulty, right? Earlier I said it's very, very hard to concentrate these minerals, primarily due to that ultrafine particle size. Fortunately, though, Dr. Yoon and his team have developed a really revolutionary technology for fine particle separation. And this is why I'm glad Mohit's on the call, because he's the expert on this. And I know Dr. Yoon probably presented on this when he gave his lecture last year. It's called the two-liquid flotation process. And the idea is based around conventional flotation, but rather than using air as your collector of hydrophobic particles, you use oil droplets. And you can show thermodynamically that oil droplets are a superior collector than air bubbles based on the contact angle that forms between air in the particle versus oil in the particle. And so with that technical understanding, we've designed a process that uses recyclable oil as the collector in flotation to separate hydrophobic and hydrophilic minerals. And it's a pretty simple flow sheet. It's a mixing tank, a phase separator, a deemulsifier that we call the Morganizer that breaks up the emulsions that form and then allows kind of a cleaning action to clean out any additional refuse and entrained water. And what you're left with after that is a organic phase, or in the oil phase, the hydrophobic particles are dispersed in the oil phase. You filter out the hydrophobic particles, and you're left with a very dry and very pure mineral sample, almost a clean black and white split on hydrophobic versus hydrophilic particles. We've demonstrated this at various scales, including lab, bench, and we're currently building a pilot scale. There's also a commercial demonstration of a very similar process that uses the same mechanism for separation. So it's a pretty robust process in terms of what it can do. And what we've done through the research here is kind of tune this to address those tiny rare earth grains that are associated with the clays and coals. All this to say, you can see that some of the advantages here of what two liquid flotation provides over traditional flotation is an incredibly robust lower particle size limit. We like to say there's no lower size limit that we found yet. Your products are always a very high grade. You can also produce dry products, which may not always be necessary, but for things like coal separation, the ability to produce a fine dry product is a huge benefit. And then the no cost of the heat of vaporization, because you're displacing the water, not evaporating the water. Show you some of the data though. So this was some of the early work we did on attempting to concentrate rare earths from coal-based refuse. And you can see here on the left side the impact of grind size. So going from a 35 micron grind size down to a 3.9 micron grind size, allows you to concentrate something from, say, 3,000 parts per million up to closer to 9,000 parts per million, while you increase your recovery from 10% up to say 50%. So this confirms that this ultrafine grinding is essential, right, to get the necessary liberation. But at the same time, it shows the process is capable of doing a pretty significant concentration, right? Taking something from 200 to 300 parts per million up to close to 10,000 or 1% rare earths. You then begin to have a viable resource at this rate. We also looked at different sample types, and you can see some of these responded better than others. One, the leatherwood thickener underflow in eastern Kentucky, we were actually able to concentrate it up to close to 2% rare earths, right, using this two liquid flotation process. So quite amazing, but once again, brutal facts. Grinding coal refuse down to single-digit microns is going to be prohibitively expensive. And this is some work I did early on to say this is very, very challenging. And so we considered an alternative approach. And this is where I go back to Jim Collins. Understanding your brutal facts allow you to then identify viable solutions. And so one of the ones we're looking at, and we're actually currently investigating, is not grinding, right? Not using actually like a stirred mill or a ball mill grinding, but using what we call blunging or dispersive liberation. And so in the clay industry, blunging is what they do to actually liberate mineral grains from kaolinite clays. And here's a picture of a plunger. It's a mixer, and then you add a polyelectrolyte dispersant to help disperse things. So it becomes more of a chemical, and it's a combination of chemical and mechanical energy to do the dispersion rather than just the impact of the balls. And what we found in some controlled tests were that actually, like for the same type of material, blunging outperforms grinding, right? So ultrafine grinding in this case was able to get up to a little bit over 1,000 parts per million, but at an abysmally low recovery, whereas the blunging curve was able to beat that. And we're currently working on a project now where we're evaluating a whole range of different chemical reagents and blunging techniques. But the underlying principle is that if we can successfully liberate it through a blunging process, the two liquid flotation process on the back end can clean it up and produce a very high grade product. And so this begins to give you a route where you can envision that next generation coal supply chain coming to life, right? Because we have an enabling technology that allows us to upgrade the resource to a point where it could be then extracted and concentrated. With that, I'm gonna skip down to my final thoughts. So a couple things. One, I want to leave you with two primary final thoughts. Hopefully this presentation was good. The first one I like to show is I showed this data before, but I'll show it this way because it's a lot more alarming when you look at it this way. This is the relative size of the mine materials, right, that are produced. And this was from Visual Capitalist. I don't know if any of you work for Visual Capitalist, but they have a good mining person because they always have really nice mining diagrams. And what this shows is, like, most of the metals that produce, you see up here, really big global iron ore. The amount of iron ore that's mined trumps everything else pretty much put together. I don't even show crushed stone. If you looked at crushed stone across the globe, it's hard to even know how much crushed stone is mined. The US alone, it's about the size of the iron ore block, right? And then if you add all the other developed countries and developing countries, crushed stone would be another slide over here. That down there is rare earths, right? And I think we need to keep this perspective when we think about how we train researchers and how we train students, right? I'd like everyone, I do think we have to build a very robust critical minerals workforce, right? But working at the university, understanding that a lot of my students are still going to be working in iron ore, they're still going to be working in crushed stone, they're still going to be working in aluminum and copper, and ensuring that when we educate students, this picture is in the back of our mind, because this will tell us where a lot of these people will end up getting jobs and end up having very successful careers. The best way I heard it told to me, and I can't take credit for this, this was gentleman at Colorado School of Mines. He said, if you think about the cake, right, we're building the cake, we're baking a cake. The rare earths are the cinnamon in the cake, right? And they're not the flour, they're not the milk, they're not the eggs. That's the crushed stone, the iron, the copper, right? That's the big parts of the cake. But the cake is pretty bland without the cinnamon in it. And that's the way the industry is, and that's the way the world is. These technology metals, very small, used in very potent doses, but they add the flavor to the world that we enjoy. At the same time, though, when we educate and think about students and think about training, I like to keep this in the back of my mind and also show this to the students as well. And on that note, I'll show you something I'm very proud of, and we've made it a very deliberate point to try to retrain the critical minerals workforce. And when I think about all the challenges in the critical mineral space, and we've looked at a lot of them today, both economic realities, technical challenges, I still think the people challenge is the one that gives me the most heartburn, right? We need a very well-trained and robust critical minerals workforce that I know, at least in the US, is lacking right now. We lack the talent we need to deploy a critical minerals industry. And so we take a very deliberate approach to how we're gonna develop that talent. And these were some news articles that my department put out over the last year. So we had one really good one on how green technologies are going to require mine materials and how we're going to need a workforce. And this was kind of the advertisement, right? We sent this one out and said, hey, here's what we're trying to do. And then just this last summer, the summer's concluding. This article was written just a couple weeks ago. I hired 6 interns into my lab, undergraduate interns, not just from mining and minerals engineering, but from all engineering disciplines across my college. So chemical engineering, industrial engineering, geosciences, mechanical engineering, and I had them work on critical minerals projects, right? And then we were able to write this article about their experience that they gained and the appreciation they learned, and what they learned about the critical minerals industry through that experience. So with that, I've probably overstayed my welcome on the call, but it's been an absolute pleasure. My name's Aaron Noble. My contact information is on the screen, and I'll be happy to stick around and answer any questions that might remain.
Thank you, Aaron. That's fantastic. Really good. No worries. I think most of the people are still here. Anyone who wants to stay for questions, please do. Either just unmute yourself or type something into the chat if you don't want. So I guess I had a question, right? So you have this physical separation by a flotation, then you have your leaching and selective precipitation, and you showed the light rare earths, like 95% pure concentrate, heavy rare, something like that. So how much of the upgrade comes from the physical processing versus the selective? I presume it's a selective precipitation. Yeah.
Yeah, so that's a great question. Thank you. And I'll answer it on the 2 contexts, right? So the first one, I think the slide you're referring to was with the acid mine drainage as a feedstock.
Yeah, okay.
That initial stage of precipitation is actually like a 2000x increase, because it starts as a very dilute solution, right? It's usually actually fractions of a part per million, like maybe half of a part per million of rare earths in solution. And then we do a stage precipitation to concentrate that up to about 1% in a solid phase.
Yep.
So you go from like half a part per million in a liquid phase to like 1% in a solid phase. That's several orders of magnitude of concentration. However, it's like in the rare earths industry, it's the question is not what you're concentrating, but it's like what's left over, right? And so that like getting rid of the additional contaminants is actually the more challenging separation. So it's like it's pretty easy to concentrate up to that, that 2000x increase. The hard is like getting rid of the contaminants, and some of them are very sticky contaminants that like to go with the rare earths. So things like zinc will partition with the rare earths, and that's where I think the more challenging separation comes in. The other example with the clays, it follows a very similar logical pathway where we start out with like this dilute, pretty much a dilute solid, and then we're able to physically concentrate that up to something like 1%. There you're doing the same thing. So that initial stage of pre-concentration, you're moving up several orders of magnitude in concentration. That's also where you get the biggest cost reduction, right? Because you can remove all your waste as early as possible using the cheapest process possible, and that allows you to then do more exotic things downstream.
And so that's a flotation step. Is that in the
Yeah, so the preferred route for like the clays is the two liquid flotation, the process that Dr. Yoon has invented and pushed forward because it can handle the small particle sizes so effectively. And I think for many years we were stumped on how to concentrate rare earths in coal-based materials because we knew the grain size was so small, we knew the liberation was challenging. And the people, it's funny that our research sponsors are always like, oh, you can just go use conventional technologies. And we're like, there's not really a good conventional technology to do 1 micron separations, right? And so we were able though to develop from that and kind of tune that out. And that's one of the real, I think, advantages of the two liquid flotation is the ability to handle those submicron particles so effectively.
Thank you. Kevin, do you have a question or comment? Or
Oh, first of all, a comment. So thank you very much, Aaron. I really enjoyed it because it's probably the first complete sort of narrative I've had on this subject. We just get this generated by the government. They're the critical ones, and they're not necessarily critical, but sometimes they are. And you've rationalised it. I mean, I could almost see the grant proposal playing out. You've probably written quite a few, so you've got a really good narrative and perspective around, what is a really a complex geopolitical topic. So thank you for that. Yeah, just on the clay one. So basically, you're saying, look, if you can just get all the clays out, remove the carbonaceous. Another way people remove the carbonaceous is you burn it, and so we've got a legacy of fly ash, right? Now, is that glassy material that you can't get it out of, or what's the story there?
Yeah, you've nailed the problem, Kevin, and thank you for the kind comments. First of all, I really do appreciate that. Yeah, when the Department of Energy, U.S. Department of Energy started the program, they were very, very interested in fly ash and invested a lot of resources looking at fly ash. And there are groups in the U.S. still interested in that as well. And I wish them the best of luck, and then I walk away from that because what happens? You are right. You do get a natural, like the combustion process is a natural concentration process, right? If you remove 90% of the carbon, well, you've just increased your material by 2 orders of magnitude. The problem is most of the combustion units run at a temperature that creates the cenospheres, and the rare earths get trapped in the cenospheres, and it's a glassy slag that is incredibly hard to crack. I have seen ways of doing it with like a high caustic treatment. So you put it in like 80% NaOH or 70% NaOH for long time periods. You can crack the glass, and then you can come back and leach it with a strong acid. But any time I've looked at that, it seems like a very costly process. I will say though that there's some unique opportunities because in the U.S. It's like I'm in good company here. We do some weird things in the U.S. And one of them is there are certain utilities which are mandated to like move their fly ash. So they'll have these fly ash ponds, and they have to move it to another pond, right? And a lot of times they're just taking a loader and putting it in a truck and taking it somewhere else. And it's like, because you're already rehandling it, you're creating a free source if you want to do some beneficial use, right? And a lot of times when they look at fly ash beneficial use, they think of a cement additive. And there are ways, and I think there are processes people are looking at where you might be able to isolate the pozzolanic material that could go towards cement additive versus the mineral components, which could become a rare earth, feedstock for rare earth extraction. I think those things are pretty challenging. The advantage we get in the pre-combustion material is you still see what I would call natural rare earth phases. So you still see distinct mineral grains that can be liberated and concentrated. in the fly ash material, those mineral grains are no longer there. They're encapsulated. So
Thanks. Ellen has her hand raised next. Yeah, Ellen.
Hi, Aaron. Thanks very much. That was a super interesting talk. I really enjoyed that sort of combination of science and engineering, but economics as well. I learned a lot. My question is about the rare earths that you find in those clays. You said I think you said they were distinct rare earth mineral grains, so that it's not rare earths that are complexed with the clays. What mineralogy is that? And do you still have some of the issues with the naturally occurring radioactivity that you would get with sort of processing monazite or bastnasite?
yeah, so really great question. First of all, I think if anyone's told you there's like one mode of occurrence in the clay, if I've said that, it's like we can always find a counterexample and be proven wrong. And
Sure.
So it's like there are many modes of occurrence. One thing we've seen, and I'll answer the question somewhat comprehensively. We think that there is especially in the US based, I've got to qualify this appropriately, the US based bituminous coals, there is very little, if any, kind of ion absorption type rare earth deposits on clay, right? Traditionally ion absorbed, that you could extract using ammonium sulfate. There's been some papers showing you can get modest removal. I think maybe 10% or less might be in the true like free ions that can be removed with simple ion exchange. And so that leads us to other types of mineral grains. We see monazite. We've seen xenotime on rare occasion. We've seen xenotime. We also see secondary phosphates like crandallite. So I think those are the big ones are crandallite, a lot of crandallite group minerals, and then some monazite. And then on rare occasion, we've seen xenotime. And there's a lot of, I think, hypotheses on how those formed, were they detrital or were they all, generated in place. What we know, though, is that if you try to leach it with ammonium sulfate, you're not going to get much out, but you can concentrate them. So it's like more distinct mineral grains. The question of natural occurring radioactive material, the best way to put it is what we've seen is like, because I've looked at like rare earth to uranium, rare earth to thorium ratios, it seems to be significantly lower than what you'd get in a pure monazite. Yeah. But not zero, right? So it's not zero, but a lot of the times when we have done more extensive piloting and concentration of rare earths from coal-based materials, the thorium is not problematic in terms of like radioactivity. So it's at a level that's not problematic. I don't have the numbers off the top of my head. I wish I knew better, but I've been in cases before where we've looked at it and we're like, oh, it's not problematic. I will say, interestingly, I talked a little bit about the acid mine drainage. The acid mine drainage we look at, it is always zero uranium, zero thorium. Acid mine drainage, especially in eastern coal seams, never gets low enough to mobilize uranium and thorium, so it's never in the source, and that's what makes that a very unique source, is because you have like no possibility of uranium or thorium issues.
Yep. No, thank you. That's very interesting.
Bill, do you have anything to say, or?
It's interesting that Aaron, you mentioned that the rare earths in these fly ashes end up in cenospheres. It's actually parallels what we find here. We're doing work from an old power station here in South Australia, and they keep giving us stuff. But interestingly, in the way they've got that old tailings, most of the cenospheres congregate down one end of the during the wet process. Rain, dry. It's almost like a fluidization process. And of course, these things, because they've got can have trapped air in them and etc. So they end up down the end. But the other thing was the different phases, because we have the same trouble with these supposedly ionic clay hosted rare earths, and it's a bit like laterite. It all depends on the degree of weathering. And one of my big beefs, and you've probably heard it many times too, is that companies think they've got a deposit and they quote assays as if they're recoveries, and get a lot of people investing in shares and things like that. Anything for the next announcement for the stock exchange. No, but thank you. You've it's nice that the work you're doing is really confirming a lot of things that we're doing, and that helps, gives us some confidence we're on the right tracks too. So
No, excellent. That's great to hear. I appreciate the feedback, and I think the folks at the newspaper stopped calling me because I'm too pessimistic on those things. So.
Just
Kevin,
one quick question. Is anyone looking to use peptides in some form in either of those approaches in the US?
No, I'm not familiar. It's interesting.
Okay.
Excellent discussion. Thanks. Most of the people were able to stay around. Anybody else have a question or comment there? Right.
I'll say this has been fantastic, and I appreciate everyone sticking around and listening. I'll be at the IMPC meeting next month, so hopefully we can continue some of these discussions there. I look forward to seeing you. Please introduce yourself, and hopefully at some point Kevin will let me come visit you guys, and we'll close the loop, and it'll be a good trip.
Yeah, that'd be fantastic. Yeah.
Yep.
you
Definitely.
count on that.
It'll happen. All right. Thank you very much.
Yep. Thanks, Aaron. And that's excellent. We'll see most of the rest of you probably in 2 weeks. I think, yeah, we have Jan Silliers in September 11th, the next speaker. So until then, thanks,
Okay.
everybody.
All right.
Thank you, Aaron.
Thank you.
Get a good sleep now. See ya.